Okay, problem number 3. This one's a good problem as well. Talking about the fastest land speeds by these incredibly powerful rocket-powered cars. If you see them, these rocket-powered cars, they blast right across usually a really big salt fields and sort of the dried salt lakes. They absolutely rocket through really fast. But let's do this problem. First off, it asks gives you speed and asks for how long it takes. Now speed here, don't get confused with coming up with actually finding the speed. Now in most kinematics equations you want to come up with velocity. The biggest difference between speed and velocity, speed is the scalar magnitude of velocity, so it's how much, it's the number. But in order to get a vector quantity, velocity just needs to have a speed, so a magnitude, and also a direction. So in this particular case, for us to turn this speed into velocity, we just need to give it a direction. So the direction that we're actually going to give it, so let's say the positive direction is in the direction of the car. Okay. The positive direction is in the direction of the car. Easy. All right. Let's have a look at what information we're given here. So here, it's given us speed, but because now we've given it a direction, it's actually now the velocity. So here, so because we're only given the distance, we're given velocity, because we have a direction and we want the time, we can calculate that it's average velocity. Now when you're calculating average velocity, you're assuming that in the entire time, in the entire distance, in the entire 20-kilometer distance, that the velocity is constant the whole way. In reality, it doesn't actually work that way. At one point it'll be fast and it'll reach a peak and then it'll sort of plateau and it won't go faster anymore. But when you're calculating the average velocity, okay, you want to assume that it's uniform, that it's constant. So in this one, it's constant 1090 kilometers per hour. Okay, in order to just convert that into our meters per second, you divide 1090 by 3.6, which I have previously done. It is, oh no, let's do the full working out. Let's do the full working out. Let's delete this part. Let's make it a bit more interesting. Let's do the full working out to actually calculate that. So let's do 1090 kilometers in 1 hour is the same as 1,090,000 meters over 3,600 seconds, which ends up being, let's have a look at what Mr. Clean got, 302.78. Let's get rid of that 8, make it a little bit better, 78 meters per second, which is the same here. So meters above the second, so meters per second, 302.78 meters per second. So for every second it actually travels, it travels at 302 meters for every second. Okay, so that's our velocity, and we know here that also our displacement is 20 kilometers, which is, you just multiply that by 1,000 to get your meters, which is 20,000 meters. If we put a little comma there, 20,000 meters. So just like the problems before, we want to get how long it takes. So we want to get time in seconds. So obviously we're going to have a look at our equation is going to be V average equals displacement over time. So if we plug in those values, our average velocity, let's put it in blue, our average velocity is 302.78 meters per second, which equals our displacement. Let's put that in magenta. Our displacement is 20,000 meters over our yellow time. Oh, let's actually, I forgot to put in the meters. Meters. Okay, it's very important. So in order to rearrange that, we rearrange that to give our time term. So time equals our 20,000, so our distance, 20,000 meters divided by 302.78 meters per second. So these two cancel out. This one goes on top and becomes a positive number. So it's just 20,000 divided by 302.76, which gives you, I calculated it before, approximately 66.06, and the value here, because these two cancel out, we have 66.06 seconds. And I hope that was helpful.